Welcome to podcast number 18. This ties perfectly in with 17. Probably should have just kept them going, but decided to make it two smaller videos. But this is picking up where we left off, where we talked about chair conformations for the six-membered ring for cyclohexane. And this is going to hold for any six-membered ring where the atoms in the ring are all second row elements, namely carbon, nitrogen, oxygen. So in particular, you're going to see the same thing when you look at sugars. So if you take 311 and we're going to 330, you're going to start viewing sugars in chair conformations as well. So drawing them is imperative. You should get good at it. So I'm going to come up with two approaches. There's the artist way, if you're really good at drawing things. And then there's my way, for those of us who aren't very good at drawing things. It's a way to fake our way through it and still get a really valid picture. So for the artist in the crowd, I want you to start, and you're going to have just a few lines you're going to draw. It's just how you connect them. So you can either call this a vertical line going up, where you start in left and go up to the right slightly, or a vertical line down, start at the right and go down the left. But either way, draw that line, number one. To that, you're going to draw a parallel line, whatever distance away. But it's a pretty good idea to make it about 2 line lengths. So this length here, make it about 2 times that. You'll get used to roughly where to put it in time. You're then going to draw a roughly 90-degree angle here and a roughly 90-degree angle there. And then the last 2 lines are just connecting the dots. So you're going to connect this dot to that dot, this dot to that dot. Notice these are kind of collinear. So if you're doing it right, everything ends up essentially collinear. They're not quite collinear if you look at it, but really close. So parallel here, parallel here, parallel here. So I'm going to call this line 1 and line 4 are parallel, line 3 and line 6 are parallel, and line 2 and line 5, are parallel. So 3 sets of parallel lines, all of equal length, a roughly 90-degree angle here, roughly 90-degree angle here, and then just connect the lines to finish it. That takes care of your 6 atoms in the ring. So for it's all carbons, it's cyclohexane. If you take bio, then this upper corner will be an oxygen atom. So suddenly now I'm a biochemist. But this is OChem day, so let's stick with OChem. If you notice from the last video, there's 3 vertical ups and 3 vertical downs, known as axial orientation. So if the point is up, the axial is up. If the point is up, axial is up. If the point is up, axial is up. If the point is down, like here, axial down, point's down, so axial down, point down, axial down. So it's easiest to draw your 3 axials at a time. So up, 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 and then down, down, down. So those aren't bad. Just make note, this line is in front of this other line. So I might add just one artistic little feature if I can. Just indicating that that line is in front of the other one. Then you have to add in your equatorials, which end up being not so bad because they end up parallel to some of these. So this line here is going to have a parallel one there. This line here is going to have a parallel one there. And then this one right here is going to be parallel to this. This one here is going to be parallel to this. So these 2 lines, making that V and this V, end up having their parallel partners. So notice this is parallel to this. This is parallel to here. So now I need a parallel one there and a parallel one there. And then last but not least, you need your substituent coming off of this carbon and this carbon. Generally, we try to draw them parallel to this line and this line. So these are going to be parallel to each other and those 2 lines. So altogether, we have drawn 18 lines. 1, 2, 3, 4, 5, 6 make that ring. 1, 2, 3, 4, 5, 6 for axial down. 1, 2, 3, 4, 5, 6 for equatorial out. Note how many of them are parallel. So 1, 2, 3 parallel here. 1, 2, 3 parallel there. So the axial substituents are all parallel. The other 12 lines come in 3 sets of 4 parallel lines. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. If you're a perfectionist, you can master that. Now, for the coordination challenged, for my group, for my peers, I'm going to say forget the perfection, and let's just draw two lines that are parallel, not quite in line with one another. So make it more like you'd be making a trapezoid, not a square. I'm going to draw these, and I'm going to put a dot high and a dot low. So whatever the line is, so this one, the lower one extends on the left. So if the lower one's left, dot is high. So lower and higher, dot high, line low on the left, line high on the right, so dot low on the right. So there are the two dots. And play connect the dots. There's one connection, second connection, third connection, and fourth connection. Nice and easy. I'm telling you, it's like not as pretty as this, but it's easy. So two lines parallel, not quite overlapping. And so even with my limited artistic skills, if I do this and this, I have a decent chair. It's not perfect. And if I want to do it the other way, I do it like this, put the dot down, the dot up. Ugly as that may be, I'm okay with it. Actually, I'm not okay. I'm going to draw this one. Oop, drew it in white. That didn't do much good. Still ugly, but it's going to work. Okay. Get rid of my stuff here. And then, same story as before. Point up, axial up, point down, axial down, point up, axial up, point down, axial down, and so forth. So toss your axials in, your three up ones first, your three down ones second, and then equatorial down, make it about 109 angle, so slightly below. This one straight down, so slightly up. This one straight down, so this one would be slightly up. Straight up, so slightly down. Straight down, so slightly up, and so forth. So for instance, this one straight down, so this is slightly up. This one straight up, so slightly down. Same thing, this slightly down, so it'll be up. This slightly up, or perfectly up, so slightly down. And then the last two here and here. They're similar. This is point up on the left, point down on the right. This is point down on the left and point up on the right. It doesn't really matter. Either one will work. I'm a firm proponent of this one because I suck at drawing, so this helps me cover up that. But if you're a perfectionist, this is the way it should look. Okay. Drawing it is honestly one of those weird tasks where you'll feel like you're in an art class or a drafting class for about 2 or 3 days as you master these. I will show the boat conformation at some point in class. Not going to worry too much about drawing that one because it's just a transition state. As it passes from one chair to another, it'll go through states called twist boat, boat, and twist boat. We're going to not really focus too much on twist boat, boat, or twist boat, other than say to go from one structure to another, you have to contort, twist, twist, contort. Okay. So here's your chair conformation. Time to just obliterate this with too much information. Axial up, axial down, axial up, axial down, axial up, axial down. They alternate. So axials up, axials down, axials up, axials down, axials up, axials down. Same with equatorial. We had axial up, so equatorial down. Next one over is equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. You'll get used to these in time. So as mentioned, this is down, and it's kind of on the equator. So I have my axis ones here. Everything else is kind of on this equator. This imaginary circle that goes around it. So equatorial, because it's on this ring and it's slightly down. So if I move around, this is axial and up. This is equatorial and up. This is axial and down. So again, notice it goes from axial down. Next one is axial up. Goes from equatorial up. Next one over is equatorial down. It alternates. So if this is axial up, this one must be axial down. This is axial down, so this one must be axial up. We can do the extremes first. Axial up. So just like this one, axial up, equatorial down, equatorial down, equatorial up, axial down, axial down. So there's one in the middle, goes axial up to axial down. So this one has the axial up. This one's axial down. And then you have your respective equatorial down that goes with this one, equatorial up that goes with that one. I'm going to erase mine so you can get a clear shot at what this is. But again, weird at first, but you'll get used to drawing it. You'll get used to visualizing it. And ultimately, by the time you get into biochem, you'll be able to do sugars real easily. Okay. Flipping chair conformations. So here are my two. Like I said, point down on the left, point up on the right. Here it's point up on the left and point down on the right. These are equivalent. They're so-called mirror images. They reflect one another. As drawn, when I put substituents, they may not be perfectly reflective. But for now, hopefully you can see that. They're equally stable. Your left hand is equally stable as your right hand in I guess, a symmetrically balanced world. So I want to figure out what goes where when you ring flip, because rings will flip. In order to get substituents in a better orientation, it will have to flip to turn something from equatorial to axial or axial to equatorial. Okay, so let's just pick a point, any point. So this carbon right here, we call this carbon number 1. It ends up that this carbon number 1 is going to go from point down to point up. So it must be this one. So as long as we can correlate it. So this carbon becomes that carbon. Notice that on it, it had axial down and an equatorial up. Up stays up. So this is my up substituent. So it's going to stay on the up side. This is my down substituent, so it stays down. But when it ring flips, everything that used to be equatorial, so equatorial and up, is now axial and up. So it keeps its up, but it goes from equatorial to axial. The axial substituent goes from axial to equatorial when it flips from one to the other. Same, let's consider this carbon over here. This is the one that's point up on the right. It's now going to go down, so it becomes point down on the right. So from up to down, and this one we're down to up. Okay, again, more important to pay attention to the substituents. So let's consider this substituent here on this one next to the green. So if I move from the green to the yellow, first one I run into on my path there. So from green to yellow, it would be this right here. So this carbon is this carbon. This is up. This is up. But notice this is equatorial to begin with, axial in the end. Equatorial becomes axial becomes equatorial, but up stays up and down stays down. So up stays up, down stays down. Okay, so I'm marking the carbon with a blue circle instead of my red ring. It is equatorial and it's up because this one's pointing straight down. So this is up. Now becomes up, or now becomes axial. It stays up, remains up. So once up, once down, always down. Let's do one more. Consider this red carbon. This carbon is right next to the yellow one, so this would be that spot right here. If I put a substituent on it, I'm just going to Z. It is equatorial. This is axial up on the red one, and this is equatorial down. Again, here's the substituent. Down stays down. So when it rotates, and this it's going to contort, it's going to cause this group to go down. It's still going to be down, but now it's going to be axial down. Again, this comes with just experience. So let's go ahead and do a couple questions. So monosubstituted cyclohexane has two possible chair conformations. Consider methyl cyclohexane. So here's cyclohexane, six-membered ring, and it has a methyl. I could have picked any carbon I wanted. That could have been methyl carbon, whatever it was. We just have to pick this one here. Nothing special about it. And nomenclature-wise, it's defined because the methyl is the first carbon. Okay, so are they degenerate? Meaning, are they of equal energy? Well, only one way to figure that out. We have to draw them out. So to draw it, again, the structure, there it is drawn. What I want to do is, again, emphasize, this is two parallel lines. This one's high, so I'm going to go low. This one's low, so go high. And I connect the dots. I've chosen this carbon because it's nice and easy. It's right there. So this is axial up. This is equatorial down. When it ring flips, I'm going to have to do the exact opposite. So now I'm going to have to make my line long on the left, or long low on the left, up there and up there. So this carbon is now point down. So let me stay with the blue. This is still down, but now axial. This is still up, equatorial for my CH3. Okay, I'm going to get rid of my drawing and let the better handwritten drawing come in. So they're up no matter what, but equatorial. So the question is one better than the other? Is axial better? Is equatorial better? So it ends up, if you were sticking straight up, there's an outside chance you could run into. Now, H's aren't that big, but the CH3 has an H, so let's draw it like this. There's an outside chance those H's can start colliding. So axial is going to run into things more often than equatorial. So axial is a less preferred position if you have steric hindrance. If it's a bulky group, you prefer to put your bulky group equatorial where it can stick out by itself and not have diaxial interactions. Okay, so we're going to look at down these two bonds and look at those interactions and see how strong they are. So sorry to have clicked so fast on that one. Okay, so what we need to do is, again, look down those interactions. Sorry for the silence, but we are lagging on the screen, unfortunately. So there we go, perfect. Okay, so within this, what we're saying is you want to look down this carbon-carbon bond and this carbon-carbon bond, this one and this one, to make a decision of where things are. And what you'll notice, if I focus on this one right here, then I'm just going to draw this Newman projection side here, CH3, H, and then the rest of the ring, the H, and the rest of the ring. Okay, on this one, where I run into trouble, is this CH3, which, excuse me, is now back. Well, considering these two H's here. And then the rest of the ring system. So that's the rest of the ring there, that's the rest of the ring there. The problem is that you start getting on this front one, I'm gonna have another H right here, axial H. That's where this one interferes. These two groups here cause steric hindrance. This CH3, on the other hand, because equatorial, is nowhere near bumping into this axial, this other equatorial. So it's far enough away that you have gauche interactions, but that's it. Here you actually have interfering interactions. They're not eclipse because they're too far away carbon-wise to call it that, but they're still dihedral or diaxial interactions. Okay, here's hoping I haven't made this so messy and so ugly you can't see it, but those interactions are the ones you're worried about. So I'm going to get rid of everything I've drawn and simply say that this axial up right here is going to potentially interfere there. Whereas this is not going to interfere, and this one is not going to interfere with the CH3. Okay. So I'm going to migrate on. So again, I'm going to look a little more carefully at all these interactions. So just going to focus on these carbons and these carbons. Going to kind of ignore the middle ones just for the time being. So again, I want to emphasize the Newman projection that we were drawing had CH3 in back, check, had H in back, check, had H in front, check, and had H in front, check. So this bond right here is this one. This is the gauche interaction I'm worried about with the ring system. And I'm also worried about the diaxial, interaction of that H and that CH3. So this is the issue you're dealing with. That gauche thing, that gauche interaction here can result in that interference there. When it's on the other position, so I go in front, notice that it is now axial to this, or I should say anti, excuse me, because equatorial, it's now anti to this, it's opposite side. And again, these H's are not going to interfere. They're not going to have any issue with the H's there, nor that one there, nor that one there. So equatorial is your more stable position based on something called steric hindrance. So a lot of work to go through that and learn how to draw these. So again, this is one of those things that comes with practice. I hope this, if you can slow it down and go through it, hope it's clear enough. If not, please come to office hours and get these things squared away. But this ends another Toddcast. So we will pick up next. Again, we're staying on cyclohexane on a couple of these, but next one is going to focus more on making predictions of relative group sizes, how much it'll interfere. So see you in the next podcast.